Hello there, and welcome. Tonight we descend into a world that remains more mysterious than the surface of the moon. A place where darkness is absolute, where pressure would crush any unprepared visitor, and where life has found ways to flourish that challenge everything we thought we knew about existence itself. The deep ocean. Let your breathing slow as we begin this journey. Allow your mind to drift downward, past the sunlit surface, through layers of blue that grow ever darker, until we reach a realm where the rules of the world above no longer apply. Here, in the cold embrace of the abyss, wonders beyond imagination wait in patient silence. Picture yourself beginning a descent from the ocean's surface. The first few meters are familiar, filled with the play of light on water, the gentle sway of currents, the dance of fish in schools that shimmer like liquid silver. But as you continue downward, something changes. The blue deepens, the light weakens, the water grows colder against your skin. You are entering a transition zone, leaving behind the bright surface world and approaching a frontier that few have crossed. This is the beginning of a journey that will take you to places more alien than any distant planet, yet they exist right here on Earth, beneath the waves that roll across 3/4 of our world's surface. The deep ocean begins where sunlight fades into memory. Scientists define it as any depth below 200 meters, the point where light can no longer penetrate with enough strength to support photosynthesis. At this boundary, the familiar ocean transforms into something entirely different. The temperature drops sharply. The pressure begins its relentless increase, and the creatures that inhabit these depths bear little resemblance to those swimming in the shallows above. This threshold marks the entrance to the largest habitat on Earth, a vast three-dimensional space that stretches from continental shelves down to the deepest trenches, covering more than 60% of our planet's surface. To cross this boundary is to leave behind the world of light and enter a domain where darkness reigns eternal. The deep ocean holds approximately 1.3 billion cubic kilometers of water. To comprehend this volume strains the imagination. It is water stacked upon water, layer after layer, extending downward for miles in many places. If you could somehow remove all this deep ocean water and spread it across the United States, it would create a layer more than 9 miles deep, drowning mountains and valleys alike beneath an incomprehensible weight of liquid. This vast volume represents the majority of all living space on our planet. Compared to the thin layer of atmosphere we inhabit or the surface of the land, the deep ocean offers living space on a scale that dwarfs all terrestrial environments combined. Most of the ocean lies in perpetual darkness. Beyond 1,000 meters deep, no trace of sunlight reaches. The water becomes a void so complete that human eyes, even fully adjusted, would see nothing at all. This aphotic zone, as scientists call it, extends downward for miles in many places, a lightless cathedral of water where the only illumination comes from the creatures themselves. In this blackness, time loses meaning. There are no days or nights, no seasons marked by changing light, only the slow currents moving through the cold, the steady rain of organic matter drifting from above, and the occasional flash of bioluminescence breaking the monotony of endless dark. For billions of years, this darkness has remained undisturbed, a constant feature of our planet long before humans ever looked upon the sea. Between the sunlit surface and this total darkness lies the twilight zone, a realm of perpetual dusk. From 200 meters to 1,000 meters deep, this mesopelagic region receives only the faintest traces of light filtering from above. It is a world of shadows and silhouettes, where creatures must have extraordinarily sensitive eyes to detect anything at all. The light that reaches here is predominantly blue, all other wavelengths having been absorbed by the water above. This creates an environment bathed in a ghostly blue twilight, dim enough that humans would struggle to see, but bright enough that it shapes the strategies of predators and prey. Many creatures perform daily migrations through this zone, rising toward the surface at night to feed under cover of darkness, then descending during the day to hide in the twilight shadows where visual predators from above cannot easily spot them. The twilight zone contains more fish than all other parts of the ocean combined. Recent research using advanced sonar systems has revealed that the biomass in this zone exceeds previous estimates by orders of magnitude. Billions upon billions of small fish, lanternfish, and bristlemouths and hatchetfish spend their days in the twilight, their silvery bodies reflecting what little light exists. Their upward-facing eyes watching for the silhouettes of prey or the descending shadows of predators. This immense population of fish represents one of the largest animal biomasses on Earth. Yet for most of history, we knew almost nothing about them. They live in a zone too deep for most surface fishing, too dark for easy observation, and too vast to survey completely. Only recently have we begun to appreciate the sheer abundance of life in this dim realm between light and darkness. The pressure in the deep ocean is almost beyond comprehension. For every 10 meters you descend, the pressure increases by approximately 1 atmosphere. At the ocean floor in many regions, the pressure reaches hundreds of atmospheres. In the very deepest parts, it exceeds 1,000 atmospheres, equivalent to having 8 tons pressing down on every square inch. To put this in perspective, if you were to stand at the bottom of the Mariana Trench, you would experience a pressure more than 1,000 times greater than what you feel standing on a beach. Your bones would shatter, your organs would collapse. The air in your lungs would compress to almost nothing. Yet despite these crushing forces, life not only exists, but thrives in abundance. Understanding pressure requires understanding the weight of water. Water is heavy. A single cubic meter weighs 1,000 kilograms, more than a ton. Now imagine stacking these cubic meters one atop another, thousands of them, a column of water extending miles into the sky. The weight of all that water presses down on everything below. At 2,000 meters deep, a depth easily reached in many parts of the ocean, the pressure equals roughly 200 atmospheres or 3,000 pounds per square inch. A human body suddenly exposed to such pressure would be destroyed instantly. The air spaces in our lungs and sinuses would collapse. The gases dissolved in our blood would behave unpredictably. Our cell membranes, designed to function at surface pressure, would fail under the strain. We are creatures of the surface, wholly unsuited for the deep. Yet the deep ocean teems with creatures that experience this pressure as normal. For them, what would kill us instantly is simply the way things are, the background condition of existence. These animals have no air spaces in their bodies to collapse. Their cells contain special molecules that prevent proteins from denaturing under pressure. Their body fluids have the same pressure as the water around them, creating an equilibrium that prevents them from being crushed. In a sense, they do not feel the pressure at all. Just as we do not feel the weight of the atmosphere pressing down on us at the surface, deep-sea creatures do not feel the ocean pressing on them. They are in balance with their environment, perfectly adapted to conditions that would annihilate us. The deep ocean is remarkably cold. Below the thermocline, a transitional layer where temperature drops rapidly, the water maintains a steady chill of just a few degrees above freezing. In most of the deep sea, temperatures hover around 4 degrees Celsius, or 39 degrees Fahrenheit. This cold is unrelenting and permanent. Without sunlight to warm the water, and with only slow currents to circulate what little warmth exists, the deep ocean remains locked in an eternal winter. For the creatures living here, cold is not a temporary condition to be endured, but the only temperature they have ever known. Their bodies function in ways that would be impossible for warm-blooded animals, with metabolisms tuned to this frigid environment, moving with an efficiency that conserves every precious calorie. More than 80% of the ocean remains unmapped with modern high-resolution techniques. Despite centuries of maritime travel and decades of ocean research, we have barely scratched the surface of understanding what lies beneath. Traditional sonar surveys have provided basic depth information for much of the ocean, but detailed mapping comparable to what we have for land or other planets covers only about 20% of the seafloor. We have better maps of Mars and the Moon than we do of our own ocean floor. Entire mountain ranges lie hidden beneath the waves, their peaks unexplored. Valleys deeper than any canyon on land remain unmapped, and in this unexplored territory, countless species surely wait, unknown to science, living their lives in darkness that no light has ever touched. The average depth of the world's oceans is approximately 3,700 meters, or roughly 12,000 feet. This means that if you were to drain all the water from the ocean basins, you would reveal valleys and plains and mountains of staggering scale. The ocean floor is not flat, but varied, marked by features as dramatic as any found on land. Vast abyssal plains stretch for thousands of miles, their surfaces covered in fine sediment that has been settling for millions of years. Seamounts rise like underwater mountains, some reaching within a few hundred feet of the surface. And cutting through it all are the trenches, those deepest of deep places where the ocean reaches its maximum depth. The Mariana Trench holds the record as the deepest known part of the ocean. Located in the western Pacific Ocean, this crescent-shaped depression in the seafloor stretches for more than 1,500 miles. But it is the trench's depth that captures the imagination. At its deepest point, known as Challenger Deep, the ocean floor lies approximately 10,984 meters below the surface, give or take 25 meters depending on the measurement. That is almost 7 miles straight down. If you placed Mount Everest, the tallest mountain on Earth, at the bottom of Challenger Deep, its peak would still rest more than a mile beneath the waves. The pressure at this depth is equivalent to having 50 jumbo jets stacked on top of you, pressing down with unimaginable force. Challenger Deep was named after 2 ships that explored its depths. The HMS Challenger first discovered the trench during an expedition in the 1870s, using primitive-sounding equipment to measure the depth. Nearly 80 years later, the HMS Challenger 2 returned and confirmed the extraordinary depth using more advanced echo-sounding technology. The name has stuck ever since, a reminder of the courage and curiosity that drives humans to explore even the most hostile environments. Today, Challenger Deep represents not just a geographic location, but a symbol of the ocean's mysterious depths, a place so extreme that reaching it remains one of the greatest achievements in exploration. Only a handful of humans have ever descended to the bottom of Challenger Deep. The first were Jacques Picard and Don Walsh, who made the journey in 1960 aboard the bathyscaphe Trieste. Their descent took nearly 5 hours, dropping slowly through the water column as the pressure increased with every meter. When they finally touched bottom, they spent only 20 minutes there before beginning the long ascent. More than 50 years would pass before another human made the trip. In 2012, filmmaker James Cameron piloted a specially designed submersible to the bottom, becoming the first person to make a solo descent. Since then, only a few others have followed, making this journey rarer than traveling to space. The temperature at the bottom of the Mariana Trench hovers just above freezing. Despite being thousands of meters below the surface, where one might expect utter cold, the temperature remains relatively stable at around 1 to 4 degrees Celsius. This consistency reflects the thermal isolation of the deep ocean, where neither sun nor surface conditions can influence the temperature. The water is cold, but not frozen, a liquid environment that has maintained roughly the same temperature for millions of years. For the creatures living at these depths, this cold is simply the nature of existence, a constant they have adapted to through countless generations. Hydrothermal vents transform the deep ocean floor into oases of life. These underwater geysers form where seawater seeps into cracks in the Earth's crust near volcanic activity. The water heats to temperatures exceeding 400 degrees Celsius before erupting back into the cold ocean, carrying with it a rich mix of minerals and chemicals. Around these vents, entire ecosystems flourish in conditions that seem utterly inhospitable. The water is toxic, filled with hydrogen sulfide and heavy metals. The temperature swings from near boiling at the vent opening to near freezing just meters away. Yet despite these extremes, life clusters around hydrothermal vents with a density thousands of times greater than the surrounding seafloor. The first hydrothermal vent discovered revealed a world no one expected. In 1977, Scientists exploring the Galapagos Rift aboard the research submersible Alvin were investigating strange temperature readings on the ocean floor. When they descended to investigate, they found something extraordinary. Water shimmering with heat poured from cracks in the rock, and surrounding these vents was life, abundant and bizarre. Giant tube worms taller than a man swayed gently in the current. Their bright red plumes extended from white tubes. Clusters of large clams covered the rocks. Strange white crabs picked their way across the stone. The scientists watched in amazement, realizing they had discovered something unprecedented. These creatures were thriving in an environment that should have been lifeless, in darkness, in toxic water, far from any connection to the sun-powered ecosystems of the surface. The discovery of hydrothermal vents in 1977 revolutionized our understanding of life. Scientists exploring the Galapagos Rift expected to find barren rock and mud. Instead, they discovered thriving communities of bizarre creatures clustered around underwater hot springs. Giant tube worms swayed in the current, their red plumes extending from white tubes anchored to the rock. Clams the size of dinner plates nestled in crevices. Pale crabs scuttled across the volcanic stone. The discovery was astounding not just because of the abundance of life, but because of how that life survived. These ecosystems do not depend on sunlight. They exist in complete independence from the sun, the first such ecosystems ever found on Earth. Chemosynthesis powers life at hydrothermal vents. Instead of using sunlight to create energy, bacteria around the vents harness chemical energy from the minerals and compounds spewing from the Earth's interior. These bacteria oxidize hydrogen sulfide, a toxic gas that would kill most life, and use the energy released to produce organic compounds. They are the foundation of the food chain, the primary producers in an ecosystem that has no need for photosynthesis. Larger animals have evolved symbiotic relationships with these bacteria, hosting them within their bodies and relying on them for nutrition. The giant tube worm, for instance, has no mouth and no digestive system. It survives entirely on the organic compounds produced by bacteria living in its tissues. The process of chemosynthesis mirrors photosynthesis in its end result, but uses a completely different energy source. Where plants capture energy from photons of light, chemosynthetic bacteria capture energy from chemical bonds. The hydrogen sulfide emerging from vents contains stored chemical energy. When bacteria break these bonds, oxidizing the sulfide, they release energy that can be captured and used to build organic molecules from carbon dioxide. The bacteria essentially do what plants do, taking inorganic carbon and turning it into the organic compounds that form the basis of all life. But they do it in total darkness, powered by the heat and chemistry of the Earth itself, rather than the radiation of the sun. This demonstrates that life is more flexible than we once thought, capable of exploiting different energy sources to achieve the same fundamental goal of growth and reproduction. Black smokers are among the most dramatic hydrothermal vents. Named for the dark, mineral-rich water they expel, these vents create chimney-like structures that can grow to heights of 18 stories or more. The smoke is actually a cloud of metal sulfides precipitating out of the superheated water as it meets the cold ocean. These minerals accumulate over time, building the chimney upward from the seafloor. Around these black smokers, temperatures can exceed 700 degrees Fahrenheit, hot enough to melt lead. Yet just inches away, the water returns to its normal frigid state. This extreme temperature gradient creates unique habitats where heat-loving bacteria thrive right at the edge of the scalding flow. The structure of a black smoker chimney is a dynamic thing, constantly growing and changing. As mineral-laden water pours from the vent, particles of iron, copper, zinc, and other metals precipitate out, coating the chimney walls and adding to its height. Over time, the chimney can become quite tall and structurally complex, with multiple openings and internal passages. Some chimneys grow crooked, leaning like drunken towers. Others develop bulbous tops or flanges. The minerals deposited create a substrate for bacteria to colonize, and these bacterial mats in turn provide food for animals. The chimney becomes not just a geological feature, but a living structure, its surfaces covered in microbes, its crevices home to worms and crustaceans. When a chimney collapses, either from its own weight or from shifts in the seafloor, a new one often grows in its place, and the cycle begins again. White smokers are cooler cousins to black smokers. These vents release lighter-colored minerals, typically barium, calcium, and silicon compounds, at temperatures around 250 degrees Celsius. While still extremely hot, white smokers are less dramatic than their black counterparts. They tend to form smaller, more delicate chimney structures, and the communities around them differ slightly from those at black smokers. Some scientists believe white smokers may have played a role in the origin of life on Earth. The chemical conditions around these vents, with their mix of energy-rich compounds and mineral surfaces that could catalyze reactions, resemble theoretical models of how life might first have arisen billions of years ago. The deep ocean floor is covered in a fine, soft sediment called ooze. This material accumulates incredibly slowly, settling from the water column above at a rate of just a few centimeters every 1,000 years. The ooze consists primarily of the remains of microscopic organisms, tiny shells and skeletons that drifted down after death. Over millions of years, this steady rain of organic matter has built up layers hundreds of meters thick in some places. To walk on this sediment would be to sink into a surface softer than mud, a layer of ancient death that blankets the ocean floor in every direction. Preserved within these layers is a record of ocean history stretching back millions of years, a chronicle of changing climates and evolving life written in the accumulated remains of countless generations. Marine snow is the primary food source for most deep-sea creatures. This term describes the continuous fall of organic material from the upper ocean, a slow-motion blizzard of detritus drifting downward. Marine snow consists of dead phytoplankton, fecal matter, mucus, bits of dead animals, and other organic particles that clump together as they fall. The journey from surface to seafloor can take weeks or months, and along the way, much of this material is consumed by creatures living in the water column. Only a small percentage of organic matter produced at the surface ever reaches the deep ocean floor. For the animals living in the abyss, food is scarce and precious. They must make the most of every morsel, every scrap that manages to complete the long descent. Some deep-sea creatures can survive for months without eating. In an environment where food arrives unpredictably and in small quantities, the ability to endure long periods of starvation becomes essential. Many deep-sea fish have extremely slow metabolisms, reducing their energy needs to a minimum. Their hearts beat slowly. Their movements are economical. When food does arrive, perhaps in the form of a large piece of marine snow or a dead animal sinking from above, they feed voraciously, storing energy in their tissues to sustain them through the next long fast. This feast or famine lifestyle requires patience and efficiency, traits that deep-sea creatures have refined over millions of years. Bioluminescence is extraordinarily common in the deep ocean. Scientists estimate that somewhere between 75 and 90% of deep-sea creatures in the mesopelagic zone can produce their own light through chemical reactions within their bodies. This prevalence suggests that bioluminescence may be the most common form of communication on the planet, far more widespread than any form of communication used by land animals. In the pitch-black depths, light becomes a valuable tool. Creatures use it to attract prey, to find mates, to confuse predators, to communicate with others of their species. The deep ocean glows with countless tiny lights, an underwater constellation that shifts and changes as creatures move through the darkness. To witness this firsthand, as researchers in submersibles have, is to see a world transformed, where every movement triggers cascades of blue-green light. The discovery of widespread bioluminescence in the deep ocean came as a surprise. Early oceanographers expected the deep sea to be dark and largely barren, a cold desert with little life. The first deep-sea expeditions that lowered nets into the abyss brought up creatures that glowed when disturbed, their bodies containing light-producing organs called photophores. As exploration continued and submersibles allowed direct observation, researchers realized the extent of bioluminescence. The deep ocean, far from being uniformly dark, twinkles and flashes with biological light. Some creatures produce steady glows. Others flash rapidly when threatened. Still others create elaborate light displays, patterns of illumination that may convey specific messages to others of their kind. The variety of bioluminescent strategies is staggering, reflecting millions of years of evolution in an environment where light is both precious and powerful. The chemistry of bioluminescence is elegantly simple. Most bioluminescent organisms use a compound called luciferin, which reacts with oxygen in the presence of an enzyme called luciferase. This reaction produces light. With almost perfect efficiency, nearly all the energy released appears as light rather than heat. Different species use variations of luciferin and luciferase, producing different colors and intensities of light. Some creatures generate their own luciferin, while others obtain it from their diet. The color of bioluminescent light is almost always blue or blue-green, because these shorter wavelengths travel farthest through seawater. Red light is absorbed quickly by water, which is why many deep-sea creatures have evolved to produce or detect blue light specifically. Bioluminescent bacteria play crucial roles in many deep-sea relationships. Some animals, like the anglerfish, cultivate colonies of light-producing bacteria in specialized organs. The fish provides the bacteria with nutrients and a safe home, while the bacteria provide light that the fish uses to attract prey. Other creatures consume bioluminescent bacteria and concentrate them in their light organs, using the stolen light for their own purposes. These symbiotic relationships between animals and light-producing microbes demonstrate the intricate ecological connections that exist even in the deep ocean. The bacteria themselves may benefit from the relationship by gaining access to nutrients they could not obtain on their own, creating a partnership where both parties gain advantages. Bioluminescence has evolved independently at least 40 times in ocean organisms. This remarkable convergent evolution demonstrates how valuable the ability to produce light is in the deep sea. From bacteria to fish to jellyfish to squid, organisms across the tree of life have developed this capability. Each lineage arrived at bioluminescence through different genetic pathways, creating different chemical systems that nonetheless achieve the same result. The widespread evolution of bioluminescence suggests that it provides significant advantages in the deep ocean environment, advantages compelling enough that natural selection has repeatedly favored organisms that can glow. In evolutionary terms, the ability to produce light in the darkness is so useful that life has invented it again and again, each time building the capability from different molecular building blocks. The anglerfish uses bioluminescence as a lure. The most famous example is the deep-sea anglerfish, with its glowing lure dangling from a modified fin ray above its mouth. This lure contains bioluminescent bacteria that the anglerfish cultivates in a specialized organ. In the darkness, this light appears as an irresistible beacon, attracting smaller fish or other creatures toward the anglerfish's waiting jaws. The anglerfish remains motionless, conserving energy while its lure does the work of hunting. When prey comes close enough, the anglerfish strikes with incredible speed, its huge mouth creating a vacuum that sucks the prey inside. This strategy allows the anglerfish to catch food without expending energy on active hunting, an important adaptation in the food-poor deep sea. Many deep-sea fish have enormous mouths and expandable stomachs. Food is so scarce in the abyss that when a meal presents itself, it makes sense to eat as much as possible, even if that meal is larger than you are. The black swallower, for instance, can consume fish more than twice its own length and 10 times its mass. Its stomach expands to accommodate this enormous meal, creating a visible bulge in its body. Other deep-sea fish have hinged jaws that can open to extraordinary angles, allowing them to engulf prey that seems impossibly large. These adaptations reflect the unpredictable nature of food availability in the deep ocean, where a creature might go months between meals and must make the most of each feeding opportunity. The fangtooth fish has the longest teeth relative to body size of any fish. This small, fierce-looking creature grows only about 6 inches long, but its teeth are so large that it cannot fully close its mouth. The fangs are necessary for gripping prey in the darkness, preventing any captured food from escaping. The fangtooth lives at depths of up to 5,000 meters, hunting in the mesopelagic and bathypelagic zones where prey is scarce. Despite its fearsome appearance, it is harmless to humans. Its teeth, while impressive, are designed for catching small fish and shrimp, not for tearing flesh from large prey. The fangtooth's appearance reminds us that in the deep sea, evolution favors function over beauty, creating creatures optimized for survival in extreme conditions. The barrel-eye fish has a transparent head. This bizarre creature possesses tubular eyes that point upward, constantly scanning the water above for the silhouettes of prey against the faint light filtering from the surface. These eyes are extremely sensitive, able to detect the dimmest illumination. But here is what makes the barrel eye truly unique. Its eyes are enclosed within a transparent, fluid-filled dome that covers the top of its head. You can look right through its skull, see the green orbs of its eyes rotating within. This transparent shield protects the sensitive eyes from the stinging cells of jellyfish, whose tentacles the barrel eye steals to eat. The fish can rotate its eyes forward when feeding, but normally they point straight up, watching for movement in the faint twilight of the mesopelagic zone. Deep-sea creatures often have enormous eyes relative to their body size. In an environment where light is scarce or absent, eyes need to be as large as possible to capture every available photon. The giant squid, for instance, has eyes the size of dinner plates, the largest eyes of any animal except perhaps its relative, the colossal squid. These massive eyes can detect bioluminescence from great distances and may help the squid spot the approach of its primary predator, the sperm whale. Larger eyes mean more light-gathering power, which translates to better vision in the deep sea's dim conditions. For creatures living in the twilight zone, where a little light still penetrates from above, having large eyes can mean the difference between eating and starving, between spotting a predator in time to escape and becoming a meal. Some deep-sea fish have lost their eyes entirely. Below 1,000 meters, in the bathypelagic and abyssal zones, no light from the surface ever reaches. In this absolute darkness, eyes become useless, organs that consume energy without providing benefit. Some species have evolved to eliminate eyes altogether, their eye sockets reduced to shallow depressions or covered with skin. These blind fish rely entirely on other senses. They detect vibrations in the water through sensitive lateral line systems. They taste and smell with extraordinary sensitivity. They navigate by feel and by detecting electrical fields generated by other organisms. The loss of vision in these creatures is not a disability, but an adaptation, a strategic reallocation of resources away from a useless sense and towards senses that serve them better in eternal darkness. The deep ocean is home to the largest migration on Earth. Every night, countless billions of small fish, squid, jellyfish, and zooplankton rise from the depths toward the surface in search of food. This diel vertical migration can involve journeys of several hundred meters or more. with some species traveling from depths of 800 meters to near the surface. As dawn approaches, these creatures descend again, returning to the safety of the deep where predators cannot easily see them. This mass movement happens every single night in oceans around the world, involving more biomass than any other migration on the planet. The ecological importance of this migration is immense, transferring nutrients and energy between different ocean layers and supporting food webs from surface to abyss. Many deep-sea creatures are red in color. This might seem like a poor choice for camouflage, but in the deep ocean, red is the perfect color for invisibility. Red light is the first wavelength to be absorbed by seawater, disappearing within the first few tens of meters. Below 200 meters, no red light exists, which means red appears black. A red creature in the deep sea is effectively invisible unless illuminated by bioluminescence, which is typically blue-green. This makes red an excellent camouflage color. Additionally, many deep-sea creatures lack the ability to see red light, their eyes having evolved to detect only blue and green wavelengths. A few species, however, have evolved the ability to produce red bioluminescence, giving them a private spotlight visible only to themselves and their prey. The vampire squid is neither a vampire nor a squid. Despite its ominous name, this small cephalopod is actually quite delicate and harmless. It gets its name from its dark red coloring and the webbing between its arms, which resembles a vampire's cape. The vampire squid lives at depths of 600 to 900 meters in a zone called the oxygen minimum layer, where oxygen levels are so low that most other creatures cannot survive. When threatened, it inverts its body, pulling its arms over its head to expose rows of soft spines that make it appear larger and more intimidating. It can also eject a cloud of sticky, bioluminescent mucus that confuses predators. Rather than hunting live prey like true squid, the vampire squid feeds on marine snow and detritus, using its thin filaments to collect particles drifting past. The glass squid is almost completely transparent. Transparency is another form of camouflage in the deep ocean, particularly effective in the twilight zone where some light still penetrates. The glass squid's body is so clear you can see right through it. Only its eyes remain opaque, appearing as dark spots. This invisibility helps the squid avoid predators while also making it a more effective hunter, able to approach prey without being seen. Transparency requires some unusual adaptations. The squid must avoid accumulating pigments, even those used for internal organs. It must have clear tissues with minimal structures that could scatter light. And it must find ways to hide or minimize its shadow, which could give away its position from below. Giant tube worms can grow over 2 meters long. These extraordinary creatures live exclusively at hydrothermal vents, clustering in dense colonies around the mineral-rich water. They have no mouth, no stomach, no digestive system of any kind. Instead, they rely entirely on symbiotic bacteria living within their tissues. The worm's bright red plume absorbs hydrogen sulfide and oxygen from the vent water, transferring these chemicals to the bacteria in its body. The bacteria use the chemicals to produce organic compounds through chemosynthesis, and these compounds sustain the worm. This symbiotic relationship appears to be remarkably efficient, as giant tube worms can grow relatively quickly for deep-sea creatures, adding several centimeters of length per year. Their lifespan is thought to extend into the hundreds of years, though exact ages are difficult to determine, as they remain anchored to the same spot, their red plumes waving slowly in the current. Deep-sea shrimp have adapted to thrive around hydrothermal vents. Some species form dense swarms directly in the vent outflow, where temperatures can exceed 60 degrees Celsius. These shrimp have special heat shock proteins that protect their cells from thermal damage. They graze on bacteria growing on the vent chimneys, scraping them off with specialized mouthparts. Some vent shrimp have lost their normal eyes but developed light-sensing organs on their backs. These organs detect the faint infrared glow emitted by the superheated vent water, helping the shrimp stay close enough to the vent to find food, but not so close that the heat becomes lethal. The yeti crab lives on hydrothermal vents near Antarctica. Discovered only in 2005, this pale, fuzzy crab gets its name from the long setae, or hair-like projections covering its claws. These setae host colonies of bacteria that the crab may farm as food, waving its claws through the vent water to provide the bacteria with nutrients. The yeti crab's habitat is extremely specialized, found only on vents in the cold waters near Antarctica. It maintains a delicate balance, staying close enough to the vent to keep its bacterial gardens healthy, but far enough away to avoid being cooked by the superheated water. Bone-eating worms feed on the skeletons of dead whales. When a whale dies and sinks to the ocean floor, an event called a whale fall, it creates a massive food bonanza for deep-sea scavengers. Hagfish and sleeper sharks arrive first, tearing away the soft tissue. After they depart, specialized worms called osedax, or bone-eating worms, settle on the skeleton. These worms have no mouth or gut. Instead, they penetrate the bones with root-like structures that secrete acid, dissolving the bone and releasing nutrients. Symbiotic bacteria in the worm's tissues then process these nutrients. A single whale skeleton can support communities of bone-eating worms and other specialists for decades, creating a temporary oasis of life in the food-poor abyss. Whale falls are crucial to deep-sea ecosystems. These massive carcasses provide concentrated sources of nutrients in an otherwise sparse environment. A single whale carcass can contain hundreds of tons of organic material, enough to sustain scavenger communities for years. The decomposition process occurs in stages, each stage supporting different communities of organisms. First come the mobile scavengers that remove soft tissue. Then come the enrichment opportunists that feed on the organic matter, enriching the sediment around the skeleton. Finally, the sulfophilic stage begins, where bacteria decompose the lipids in the whale's bones, producing hydrogen sulfide and creating a miniature chemosynthetic ecosystem similar to a hydrothermal vent. This final stage can last for 50 years or more, making whale falls among the longest-lasting food resources in the deep sea. The colossal squid is the heaviest invertebrate on Earth. While the giant squid is longer, the colossal squid is much more massive and robust. Scientists estimate it can reach lengths of around 12 to 14 meters and weights that may approach or exceed 500 kilograms, though intact adult specimens are extremely rare and exact measurements remain uncertain. This enormous creature lives in the deep waters around Antarctica, hunting large fish and other squid. Its tentacles are equipped with sharp rotating hooks, unlike the suction cups of most squid. These hooks can rotate 360 degrees and are used to grip and slash prey. The colossal squid has eyes the size of dinner plates, with diameters that may reach up to 30 centimeters. These are among the largest eyes of any animal that has ever lived, possibly rivaling or exceeding even those of the giant squid, though comparing measurements from different specimens presents challenges. These massive eyes may help it spot the approach of sperm whales, its primary predator, in the dim light of the deep ocean. The eyes of a colossal squid are truly extraordinary organs. Each eye can be up to 30 centimeters in diameter, larger than a human head. The pupil alone can be 9 centimeters across. These enormous eyes are not mere curiosity, but essential adaptations for life in the deep ocean. With such large eyes, the squid can gather even the faintest traces of light, detecting the bioluminescence of prey or the movement of predators at great distances. The eyes may also help the squid see in different directions simultaneously, one eye watching above while the other scans below, providing comprehensive awareness in a three-dimensional environment where threats can come from any direction. The structure of these eyes, with their massive lenses and dense concentration of light-sensitive cells, represents one of nature's most impressive solutions to the problem of seeing in near-total darkness. Sperm whales are the deepest diving mammals. These magnificent creatures regularly dive to depths of over 1,000 meters and have been recorded reaching depths of 2,000 meters or more when hunting. Though the exact maximum depth they can achieve remains a subject of ongoing research. They can hold their breath for up to 90 minutes, descending into the dark in search of their favorite prey, giant squid and other large cephalopods. The whale's body is specially adapted for these extreme dives. Its lungs compress, forcing air into spaces protected by cartilage and fat. Its blood and muscles carry extraordinary amounts of oxygen, stored in high concentrations of hemoglobin and myoglobin. During the dive, the whale's heart rate slows dramatically and blood flow is restricted to only essential organs. When it finally locates prey, the whale uses echolocation so powerful that some researchers hypothesize it may stun or disorient its target before striking, though this remains debated. The battle between a sperm whale and a giant squid must be one of nature's most dramatic encounters, though no human has ever witnessed one. Based on the evidence we see on whale bodies, we can imagine how these encounters might unfold. In the darkness of the deep ocean, a whale descends, its massive body moving through the water with surprising grace. Its echolocation clicks pierce the silence, bouncing off the squid's body and revealing its location. The squid, sensing danger, may try to flee or may turn to fight. Its tentacles, armed with suckers and hooks, lash out. The whale's skin bears scars from countless such encounters, circular marks left by squid suckers. Sometimes squid beaks are found lodged in the whale's flesh, evidence of battles fought in the abyss. From these clues, researchers infer that the whale must grab the squid in its narrow lower jaw, lined with conical teeth, avoiding the thrashing tentacles while preventing the squid from escaping into the darkness. Many sperm whales carry extensive scarring from encounters with giant and colossal squid. Their skin is marked with circular scars where squid suckers gripped and tore, sometimes leaving patterns that reveal the size of the squid involved. Some scars are quite large, suggesting encounters with truly massive squid, possibly larger than any specimen recovered by scientists. These scars tell stories of hunts in the deep ocean, of battles fought in complete darkness, of predator and prey locked in struggles that determine survival. The fact that whales continue to bear fresh scars throughout their lives indicates that they hunt squid regularly, diving again and again into the abyss. Despite the wounds they receive, the squid, for their part, must see the approaching whale as a threat of unimaginable size, a monster descending from above with the power to end their existence in seconds. The pressure adaptations of deep-sea fish are remarkable. Unlike mammals, which must carefully manage air spaces in their bodies, many fish have no air spaces at all. Their swim bladders, if present, are filled with lipids or other incompressible materials rather than gas. Their bodies are composed largely of water, which does not compress under pressure. This means the pressure inside their bodies equals the pressure outside, preventing them from being crushed. Many deep-sea fish also have flexible, cartilaginous bones rather than rigid, calcified ones. Their flesh often has a gelatinous consistency, which allows them to withstand pressure that would destroy animals with more rigid bodies. TMAO is crucial for deep-sea survival. Trimethylamine N-oxide is a small organic molecule that deep-sea fish accumulate in their cells in high concentrations. This compound counteracts the damaging effects of pressure on proteins and cell membranes. Under extreme pressure, proteins can denature and lose their function, and cell membranes can become too rigid. TMAO prevents these problems by stabilizing protein structures and maintaining membrane fluidity. The deeper a fish lives, the more TMAO it accumulates in its tissues. This elegant molecular solution allows life to exist at pressures that would otherwise be lethal. Interestingly, TMAO is what gives fish their characteristic fishy smell. So the smell of the sea is partly the smell of pressure adaptation. Abyssal gigantism is a phenomenon where deep-sea creatures grow larger than their shallow water relatives. Giant isopods, for instance, can grow to the size of a football, while their shallow water cousins are typically a few centimeters long. Deep-sea amphipods, spider crabs, and certain jellyfish also exhibit this tendency toward gigantism. The causes are not fully understood, but several factors likely contribute. The cold temperatures in the deep ocean slow metabolism, which may allow organisms to live longer and grow larger. Lower predation pressure might remove size constraints. The scarcity of food might favor larger bodies with more efficient metabolisms. Whatever the cause, the result is creatures that seem to dwarf their shallow water counterparts, living examples of how the deep ocean shapes life in unexpected ways. The Hadal Zone is the deepest part of the ocean. Named after Hades, the Greek god of the underworld, this zone includes ocean depths below 6,000 meters. Hadal zones are found primarily in deep trenches formed where tectonic plates collide. Life in the Hadal zone must contend with the most extreme pressures on Earth, often exceeding 1,000 atmospheres. Yet even here, at the absolute limits of the ocean's depth, life persists. Snailfish have been found living below 8,000 meters. Amphipods scuttle across the seafloor at depths exceeding 10,000 meters. These creatures represent the frontier of life's adaptability, surviving in conditions that seem almost incompatible with biology. The Hadal snailfish holds the record for the deepest living fish ever observed. This small, translucent fish has been recorded at depths greater than 8,000 meters in the Mariana Trench and other Hadal zones. It has no scales, its body almost transparent, and it moves with an otherworldly grace through the crushing pressure. The Hadal snailfish's genome reveals special adaptations for pressure tolerance, including modifications to proteins and cell membranes that allow them to function under extreme conditions. This creature lives at the very edge of where fish can survive, in a realm so extreme that only highly specialized organisms can exist. Amphipods are among the most abundant creatures in the Hadal zone. These crustaceans, resembling tiny shrimp, have been found at depths exceeding 10,000 meters, with some specimens recovered from near the bottom of the Mariana Trench itself. Some Hadal amphipods grow quite large, reaching lengths of over 30 centimeters. They are scavengers, feeding on organic material that sinks to the seafloor, and on the occasional larger food, falls like dead fish or marine mammals. Baited camera traps have captured images of swarms of these amphipods converging on bait within hours, demonstrating that even at extreme depths, scavengers respond quickly to food opportunities. The temperature at hydrothermal vents can exceed 400 degrees Celsius in the fluid emerging from the vent itself. Yet the water does not boil because the enormous pressure at these depths raises the boiling point of water far above its normal value. This superheated water, sometimes reaching temperatures as high as 400 degrees or more at black smokers, erupts from the seafloor carrying dissolved minerals that precipitate when the hot water meets the frigid surrounding ocean. The chemical-rich water supports ecosystems unlike any others on Earth. The discovery of these ecosystems forced scientists to reconsider fundamental assumptions about the requirements for life. Previously, it was thought that all life on Earth ultimately depended on sunlight. Hydrothermal vent communities proved that wrong, showing that life can exist independently of photosynthesis. Some scientists believe life on Earth may have begun at hydrothermal vents, though this remains one hypothesis among several. The conditions at these vents, with their abundant chemical energy and mineral-rich environments, resemble some theoretical models of early Earth. The chemicals dissolved in vent water can undergo reactions that produce organic molecules, the building blocks of life. Mineral surfaces around vents could have catalyzed these reactions, concentrating and organizing molecules in ways that eventually led to self-replicating systems. Additionally, vents would have provided shelter from the meteorite impacts and harsh radiation that characterized Earth's surface 4 billion years ago. While the origin of life remains one of science's great unsolved questions, hydrothermal vents offer a compelling scenario for how life might have first emerged on our planet. Deep-sea sediments contain a vast archive of Earth's climate history. The ooze that blankets the ocean floor accumulates slowly and steadily, preserving a record of conditions in the ocean over millions of years. Scientists drill cores from this sediment and analyze the shells of microscopic organisms preserved within. The chemical composition of these shells reveals information about ocean temperature, salinity, and chemistry at the time the organisms lived. By analyzing sediment cores, scientists can reconstruct past climates, tracking ice ages and warm periods, changes in ocean circulation, and variations in atmospheric carbon dioxide. The deep-sea sediment record extends back tens of millions of years, providing a continuous archive longer than any on land. Manganese nodules cover vast areas of the abyssal plain. These potato-sized lumps of metal-rich minerals grow incredibly slowly, accumulating layers at a rate of millimeters per million years. They contain manganese, iron, nickel, copper, and cobalt. The nodules form when dissolved metals in seawater precipitate around a nucleus, often a shark tooth or piece of shell. Over millions of years, layer upon layer builds up, creating these dark, rough-textured lumps. Some areas of the ocean floor are carpeted with manganese nodules stretching to the horizon. The prospect of mining these nodules for their metal content has generated both interest and concern, as harvesting them would destroy ancient and poorly understood deep-sea ecosystems. Deep-sea mining poses serious threats to ocean ecosystems. The deep ocean floor hosts unique communities of organisms, many of them undiscovered by science. Mining operations would destroy these habitats directly by removing sediment and nodules, and indirectly by creating plumes of suspended sediment that could spread for hundreds of kilometers. The creatures living in these environments are often slow-growing and may take decades or centuries to recover from disturbance. Some ecosystems, particularly those around hydrothermal vents, are home to species found nowhere else on Earth. Once destroyed, these unique habitats may be gone forever. As technology makes deep-sea mining more feasible, the tension between resource extraction and conservation becomes increasingly urgent. The ocean's midnight zone is the largest habitat by volume on Earth. This zone, from 1,000 to 4,000 meters deep, contains more living space than all terrestrial environments combined. Yet despite its vast size, the midnight zone remains remarkably understudied. Most of what we know comes from brief glimpses captured by research vessels and submersibles. The creatures living here are adapted to life in eternal darkness, with many producing bioluminescence. The midnight zone serves as habitat for countless species, acts as a highway for migrating animals, and plays a crucial role in ocean food webs, by recycling nutrients and carbon. Plastic pollution has reached the deepest parts of the ocean. In 2019, explorers found a plastic bag and candy wrappers at the bottom of the Mariana Trench, nearly 11,000 meters below the surface. This disturbing discovery demonstrates that human influence extends even to the most remote places on Earth. Microplastics have been found in the guts of deep-sea creatures, showing that pollution has entered deep-sea food webs. The long-term consequences of this pollution remain unknown, but the presence of synthetic materials in the deepest ocean trenches serves as a stark reminder that there is no part of Earth untouched by human activity. Deep-sea corals can live for thousands of years. Unlike their shallow water relatives that depend on symbiotic algae, deep-sea corals survive by filter feeding on organic particles and zooplankton. They grow extremely slowly, sometimes adding less than a millimeter of skeleton per year. Radiocarbon dating and other techniques suggest that some deep-sea coral colonies may be over 4,000 years old, placing them among the oldest living organisms on Earth. Though dating ancient corals presents significant challenges. These ancient corals provide habitat for numerous other species, creating biodiversity hotspots in the otherwise sparse deep ocean. Unfortunately, bottom trawling and other fishing practices have damaged many deep-sea coral communities, destroying in minutes what took millennia to build. Seamounts are underwater mountains that rise from the ocean floor. These submerged peaks, which may reach within a few hundred feet of the surface or remain well below it, are hotspots of biodiversity. Currents flowing over seamounts bring nutrients from deep water to shallower depths, creating feeding opportunities for filter feeders. Many seamounts host dense colonies of deep-sea corals, sponges, and other attached organisms. Fish aggregate around seamounts to feed, rest, or reproduce. Because of this abundance, seamounts are often targeted by fishing operations, particularly for orange roughy and other deep-sea species. Overfishing has damaged many seamount ecosystems, raising concerns about protecting these important habitats. The orange roughy can live for over 100 years. This deep-sea fish grows very slowly and does not reach reproductive age until it is 20 to 30 years old. These life history traits made it extremely vulnerable to overfishing. When orange roughy fisheries first developed in the 1980s and 90s, catches were initially high, but populations crashed rapidly. The fish could not reproduce quickly enough to replace those being caught. Many orange roughy populations remain depleted today, decades after fishing pressure was reduced. The orange roughy story serves as a cautionary tale about the vulnerability of deep-sea species, which often have slower life cycles than their shallow water counterparts. Greenland sharks may be the longest living vertebrates on Earth. These massive sharks, which can reach lengths of 6 meters or more, inhabit the deep, cold waters of the Arctic and North Atlantic. They grow extremely slowly, perhaps 1 centimeter per year, and take over a century to reach sexual maturity. Recent research using radiocarbon dating of eye-lens proteins suggests some Greenland sharks may live 400 years or more, with one individual estimated to be around 512 years old. Though such age estimates come with significant uncertainty, This extraordinary longevity, if confirmed, would make them the longest-lived vertebrates known to science, reflecting the slow pace of life in the cold, deep ocean. The Greenland shark moves slowly, saves energy, and grows at a glacial pace, but in doing so achieves a lifespan longer than any other vertebrate known to science. The deep ocean is largely silent compared to surface waters. Sound travels well in water, better than in air, but the deep sea is relatively quiet. There are no waves breaking, no rushing currents in most areas, no large populations of vocal animals. The soundscape consists mainly of the occasional click of echolocating whales, the slow creak and groan of the Earth's crust, and the subtle sounds of deep currents moving through underwater canyons. This silence contributes to the alien quality of the deep ocean, a place where the normal sounds of the living world are largely absent. However, sound is important for some deep-sea creatures. Sperm whales use powerful clicks for echolocation, sending out pulses of sound that bounce off prey and reveal its location. These clicks are among the loudest sounds made by any animal. Some deep-sea fish may produce sounds to communicate, though this remains poorly studied. Human-generated noise from shipping, oil exploration, and military activities penetrates even into deep waters, potentially disturbing creatures that evolved in a quiet world. The long-term effects of this noise pollution on deep-sea ecosystems remain largely unknown. Deep-sea fish often have weak muscles and bones. In an environment where food is scarce and every calorie must be conserved, maintaining a heavy, energy-intensive body is a disadvantage. Many deep-sea fish have reduced bone density, with skeletons that are thin and flexible rather than thick and rigid. Their muscles are often underdeveloped, containing more water and connective tissue than the muscles of more active fish. This reduced musculature gives them a flabby appearance when brought to the surface. But in their natural environment, these fish are well adapted to life at depth. They do not need to swim fast or far, so powerful muscles would be wasteful. Instead, they drift slowly, conserving energy, waiting for food to come to them. The challenge of exploring the deep ocean cannot be overstated. It is, in many ways, more difficult than exploring space. The pressure alone creates enormous engineering challenges. A spacecraft must contain 1 atmosphere of pressure within its walls and withstand 0 atmospheres outside. A deep-sea submersible must contain 1 atmosphere within and withstand hundreds of atmospheres outside. This means the pressure differential is far greater, requiring incredibly strong materials and careful design. Add to this the corrosive nature of seawater, the complete darkness, the cold, and the distance from support, and you begin to understand why deep-sea exploration remains so challenging, even with modern technology. The history of deep-sea exploration is one of incremental progress and occasional breakthroughs. In the 19th century, oceanographers used weighted lines to measure depth, dropping them overboard and waiting for them to hit bottom. This method was slow and imprecise. The invention of sonar in the early 20th century revolutionized depth measurement, allowing ships to map the ocean floor while moving. But actually seeing the deep ocean, observing it directly, required sending something down there. Early attempts used dredges and trawls, blind devices that scraped across the seafloor and brought up whatever they caught. These revealed that life existed in the deep ocean, but gave little sense of what that life was like in its natural environment. The bathysphere represented a major advance. Invented in the 1930s, this spherical chamber could carry observers to depths of several hundred meters. It hung from a cable attached to a ship on the surface, with occupants peering out through small windows made of thick quartz. The bathysphere was claustrophobic and dangerous. If the cable broke, the occupants would sink to the bottom with no way to return. But it allowed the first direct observations of deep-sea life, giving scientists their first glimpses of creatures that had previously been known only from damaged specimens brought up in nets. The bathyscaphe improved on the bathysphere design. Unlike its predecessor, the bathyscaphe was self-propelled and could return to the surface even if its connection to a support ship was severed. It used gasoline for buoyancy, as gasoline is less dense than water and doesn't compress significantly under pressure. Iron ballast weights could be dropped to make the craft rise. With these innovations, the bathyscaphe could dive far deeper than any bathysphere. It was a bathyscaphe, the Trieste, that carried Jacques Piccard and Don Walsh to the bottom of Challenger Deep in 1960. A dive that reached the deepest point in the ocean and proved that life could exist even there. Modern submersibles have built on these early designs. Alvin, first launched in 1964, has undergone multiple upgrades but continues to carry scientists to the deep ocean. It has made thousands of dives, contributing to countless discoveries, from hydrothermal vents to shipwrecks to new species. Its observation windows provide clear views of the deep-sea environment. Its manipulator arms can collect samples with precision, and its design has been proven over decades of use. Other submersibles, like Japan's Shinkai and China's Fendouzhe, can dive even deeper, pushing the boundaries of where humans can directly observe the ocean. Remotely operated vehicles have expanded our reach even further. These robot explorers, connected to surface ships by cables, can dive to extreme depths while their operators remain safe above. They carry cameras that transmit video in real time, allowing researchers to see the deep ocean without the risk and expense of human-occupied dives. ROVs can work for hours or days, hovering in place or moving systematically across the seafloor, guided by operators who may be thousands of miles away. Their manipulator arms can collect samples, deploy instruments, and interact with the environment. Many of the most important deep-sea discoveries of recent decades have come from ROV expeditions. Autonomous underwater vehicles represent the latest evolution in ocean exploration. Unlike ROVs, AUVs have no cable connecting them to the surface. They operate independently, following pre-programmed routes or responding to their environment according to algorithms. This freedom allows them to explore areas where cables would be impractical, to work under ice, to map large areas efficiently. AUVs can carry sonar systems that produce high-resolution maps of the seafloor, revealing details invisible to satellites or surface ships. Some AUVs can dive to great depths, withstand strong currents, and operate for days or weeks without human intervention. As technology improves, AUVs are becoming increasingly capable, taking on tasks that once required expensive ship time and human operators. The blobfish became famous for its appearance when brought to the surface. In its natural deep-sea habitat, the blobfish appears relatively normal, its gelatinous body giving it a blob-like but not particularly unusual shape. However, when hauled to the surface, the dramatic pressure change causes the fish's body to expand and deform, creating the droopy, melted appearance that became an internet meme. This transformation illustrates how poorly adapted surface conditions are for deep-sea creatures. The blobfish evolved for life at extreme pressure, and bringing it to surface pressure is like subjecting a surface-dwelling creature to the vacuum of space. Some deep-sea fish have light organs on their bellies. This adaptation, called counter-illumination, helps the fish blend in with the faint light filtering from above. When viewed from below, a fish would normally appear as a dark silhouette against the lighter surface waters. By producing light on its underside that matches the intensity of the downwelling light, the fish can make its silhouette disappear, rendering itself effectively invisible to predators or prey below. The fish must carefully adjust the intensity of its bioluminescence to match the changing light levels as it moves up or down in the water column. This remarkable adaptation demonstrates the sophisticated ways that deep-sea creatures use light in the darkness. Deep-sea creatures have extremely efficient eyes. The eyes of some deep-sea fish are among the most sensitive light-detecting organs known. They have large lenses to gather as much light as possible and extremely dense concentrations of light-sensitive cells in their retinas. Some species have evolved unique visual pigments that are perfectly tuned to detect the wavelengths of bioluminescence produced by their prey or predators. These adaptations allow deep-sea fish to see in conditions we would consider complete darkness, detecting individual photons of light and using that minimal information to navigate, hunt, and avoid predators in the abyss. The deep ocean plays a crucial role in regulating Earth's climate. Cold, deep water stores vast amounts of carbon dioxide, removing it from the atmosphere for hundreds or thousands of years. The deep ocean also stores heat, absorbing excess warmth from the surface and transporting it through a global system of deep currents. This ocean circulation, called the thermohaline circulation or ocean conveyor belt, connects all the world's oceans and influences climate patterns across the globe. Changes in deep ocean circulation could dramatically affect global climate, making understanding the deep sea crucial for predicting future climate change. Scientists use sophisticated technology to explore the deep ocean. Remotely operated vehicles, or ROVs, allow researchers to explore depths no human could survive. These tethered robots are equipped with cameras, lights, and manipulator arms that can collect samples. Autonomous underwater vehicles, or AUVs, operate without a tether, following pre-programmed routes to map the seafloor or collect data. Human-occupied submersibles, like Alvin and the newer limiting factor, can carry researchers to extreme depths, allowing them to see the deep ocean with their own eyes. Each type of vehicle has advantages and limitations, and together they have revolutionized our understanding of the deep sea. The pressure suits used by deep-sea vehicles are engineering marvels. The pressure at deep ocean depths would instantly crush any normal vehicle. Submersibles use thick steel or titanium spheres to protect their occupants, with walls several inches thick. Windows must be specially designed, often made from acrylic or sapphire, shaped and sized to withstand the crushing pressure. Even with these precautions, every deep dive carries risk. Small imperfections in materials or construction could lead to catastrophic failure. The design and construction of deep-sea vehicles requires extraordinary precision and represents some of the most challenging engineering on Earth. Deep-sea bacteria may hold keys to new medicines. The extreme environments of the deep ocean force bacteria to produce unique compounds to survive. Some of these compounds show promise as antibiotics, anti-cancer agents, or other pharmaceuticals. Deep-sea bacteria have been found producing enzymes that function under extreme conditions of temperature and pressure, enzymes that could be useful in industrial processes. As antibiotic resistance becomes an increasingly serious problem, the deep ocean may provide new sources of compounds that can fight disease. However, studying these organisms is challenging, as many cannot be cultured in laboratories under normal conditions. The deep ocean may contain more species than any other ecosystem on Earth. Despite decades of research, scientists estimate that we have discovered only a small fraction of deep-sea species. Each new expedition typically discovers multiple species unknown to science. The vast size of the deep ocean, combined with its complex topography and diverse habitats, creates opportunities for immense biodiversity. Many deep-sea species have restricted ranges, found only in particular trenches or around specific seamounts, which increases overall species diversity. As exploration continues, the catalogue of deep-sea life grows constantly, revealing a world of astonishing variety hidden beneath the waves. Deep-sea creatures often have slow reproduction rates. Many deep-sea fish take years or decades to reach sexual maturity, produce relatively few offspring, and may reproduce only once or a few times in their lives. This reproductive strategy reflects the harsh, resource-limited environment of the deep ocean. Producing many offspring requires energy, and energy is scarce in the abyss. Instead, deep-sea creatures invest heavily in each offspring, giving them the best chance of survival in a challenging environment. This slow reproduction makes deep-sea populations vulnerable to disturbance. Once a population is reduced by fishing, pollution, or habitat destruction, recovery may take decades or longer. The deep ocean contains vast reserves of methane. Frozen methane hydrate, an ice-like substance where methane is trapped in a cage of water molecules, exists in enormous quantities in deep ocean sediments. These deposits form where cold temperatures and High pressures allow methane produced by bacteria to combine with water. The amount of carbon stored in methane hydrates may exceed the amount stored in all known fossil fuel reserves. If ocean temperatures rise, these hydrates could melt, releasing methane into the ocean and potentially into the atmosphere. Because methane is a potent greenhouse gas, this represents a potential positive feedback loop that could accelerate climate change. Understanding deep-sea methane deposits is crucial for predicting future climate scenarios. Deep-sea sediments host a vast and largely unknown community of microbes. Bacteria and archaea live in the sediments of the ocean floor, surviving on minimal nutrients and energy. Some of these microbes have metabolic rates so slow that they may divide only once every 1,000 years or more. They represent life at the very edge of what is possible, existing in a state that blurs the line between living and dormant. These sediment microbes play important roles in nutrient cycling and may represent a significant fraction of Earth's total biomass. Their discovery has expanded our understanding of the limits of life and raised questions about how organisms can survive with so little energy. Oceanic trenches form where tectonic plates collide. When one plate is forced beneath another in a process called subduction, it creates a deep trench in the seafloor. These trenches are the deepest parts of the ocean, with the Mariana, Tonga, Philippine and Kermadec trenches all exceeding depths of 10,000 meters. The walls of these trenches are steep, and the environment is extreme even by deep-sea standards. Yet life exists even in these ultimate depths, demonstrating that given enough time, evolution can adapt to almost any environment Earth provides. Slow sedimentation rates in the deep ocean mean the seafloor we see today may be ancient. In the deepest parts of the ocean, sediment accumulates so slowly that the surface you would see if you descended in a submersible might be thousands of years old. Any disturbance, whether from natural causes or human activity, affects surfaces that took millennia to form. This means impacts to the deep-sea floor persist far longer than impacts to more dynamic environments. A track left by a deep-sea mining operation or a trawl from a fishing net might remain visible for decades or centuries. The ocean's deepest point is constantly being refined with better technology. As measurement techniques improve, our estimates of the Mariana Trench's depth become more precise. Early measurements used weighted lines that could be quite inaccurate. Modern measurements use sophisticated sonar and pressure sensors. Current best estimates place Challenger Deep at approximately 10,984 meters deep, with an uncertainty of around 25 meters either way. The quest to determine the exact deepest point continues, driven by both scientific curiosity and the human desire to know the extremes of our world. Deep-sea exploration faces numerous challenges. The ocean's depth makes accessing it difficult and expensive. The pressure makes equipment design challenging. The darkness requires powerful lights that can disturb the very creatures researchers hope to observe. The remoteness of many deep-sea locations requires long expeditions on expensive research vessels. Limited funding means that deep-sea research competes with other scientific priorities. Despite these challenges, researchers continue to explore the deep ocean, driven by curiosity about Earth's last great frontier, and the understanding that the deep sea plays crucial roles in global ecosystems and climate. As we drift towards sleep, let the deep ocean remain in your thoughts. Imagine yourself suspended in that eternal darkness, surrounded by creatures that glow with their own light. Feel the pressure around you, constant and unchanging. Sense the cold that never varies, the silence that is broken only by occasional distant sounds. The deep ocean is a world apart from our own, yet it is part of the same planet we call home. It covers most of Earth's surface and holds most of Earth's water. In its depths, life persists in forms we are only beginning to understand, shaped by forces we can barely imagine, thriving in conditions we once thought incompatible with existence. Consider for a moment the sheer scale of the deep ocean. If you could somehow drain all the water from the ocean basins, you would reveal a landscape more dramatic than anything on the continents. Mountain ranges taller than the Himalayas run for thousands of miles along mid-ocean ridges. Valleys deeper than the Grand Canyon cut through the seafloor. Volcanic peaks rise from the abyss, some reaching nearly to the surface, others remaining forever submerged, crowned only by the crushing weight of water. This hidden topography shapes ocean currents, influences weather patterns, and provides habitats for countless species. It is a world we have barely begun to map, let alone understand. The deep ocean reminds us of how much we do not know. Every expedition discovers new species. Every dive reveals unexpected behaviors. Every sample of sediment or water contains surprises. We live on a planet where the majority of the biosphere remains unexplored, where entire ecosystems exist unknown to science, where discoveries that could change our understanding of life itself wait in the darkness. This should fill us with humility, reminding us that for all our technological achievement, we are still newcomers on Earth, still learning about the world we inhabit. Allow your breathing to slow. Let your muscles relax. The deep ocean will continue its silent existence through the night and through the ages, unchanged by our awareness or understanding. It existed before humans walked the earth and will exist long after we are gone. In its timeless depths, creatures will continue their ancient patterns, hunting and hiding, glowing and drifting, living lives we may never fully comprehend. And above it all, the surface world continues, unaware of the vast realm beneath, a realm that shapes our climate, produces our oxygen, and harbors mysteries we have only begun to uncover. Think of the deep ocean as a library of possibilities. Every creature there represents a solution to the problem of survival in extreme conditions. Every adaptation, from bioluminescent lures to pressure-resistant proteins to symbiotic relationships with bacteria, demonstrates life's creativity in the face of challenge. By studying these creatures, we learn not just about the deep ocean, but about the fundamental principles of biology. We discover proteins that function under extreme pressure, compounds that produce light efficiently, strategies for surviving with minimal food. This knowledge has practical applications. Deep-sea organisms have already contributed to medicine, biotechnology, and materials science. Who knows what other discoveries wait in the unexplored depths? What other solutions to problems we have not yet imagined? The deep ocean also serves as our planet's memory. The sediments that accumulate on the ocean floor contain chemical signatures that record past climates, past ocean conditions, past extinctions, and radiations of life. By drilling into these sediments and analyzing what we find, we can reconstruct Earth's history over millions of years. We can see how the planet has responded to past changes in carbon dioxide, past variations in ocean circulation, past impacts of asteroids and volcanoes. This history is not just academic curiosity. It informs our understanding of how Earth's systems work, how they respond to change, and what we might expect as our own actions alter the planet. The deep ocean sediments are an archive of Earth's past and a guide to understanding its future. Consider also the role of the deep ocean in regulating our climate today. The cold water of the deep ocean stores vast amounts of heat and carbon dioxide. Currents transport this cold water around the globe in a slow circulation that takes hundreds or thousands of years to complete. This circulation moderates climate, distributing heat from the tropics toward the poles, absorbing excess carbon dioxide from the atmosphere, and helping to stabilize Earth's temperature. Without the deep ocean's capacity to store heat and carbon, our climate would be far less stable, far more prone to rapid and dramatic shifts. The deep ocean is not separate from the core surface world. It is intimately connected, part of a single integrated system that makes our planet habitable. The deep ocean reminds us that our world still holds unknowns, still contains places we have not fully explored, still surprises us with discoveries that change our understanding of life itself. It is a frontier as challenging as space, as alien as another planet, yet it is here, beneath the waves that lap against our shores. As you drift into sleep, carry with you the knowledge that the ocean's depths remain largely unexplored, waiting for future generations to reveal their secrets, one discovery at a time. Picture one last image as sleep approaches. Imagine the ocean at night, its surface calm, reflecting the stars. Beneath that surface, the water column extends downward for miles. In the darkness below, millions of creatures perform their nightly migration, rising toward the surface to feed. Tiny bioluminescent organisms flash and glow. Jellies pulse slowly through the water. Fish navigate by senses we can barely imagine. And deeper still, in the abyss, creatures live their entire lives in conditions no sunlight has ever touched. Adapted to pressure and cold and darkness, thriving in ways that challenge everything we thought we knew about the requirements for life. This is happening now as you prepare for sleep, as it has happened every night for hundreds of millions of years. The deep ocean continues, patient and mysterious, waiting for us to understand it better. If you enjoyed this journey into the depths, consider liking this video and subscribing to the channel. Each subscription helps others find their way here. discovering calm in the exploration of Earth's hidden wonders. But for now, there is nothing more to do but rest. Let the thought of the deep ocean's vast, patient darkness carry you into sleep. Let it remind you that there is so much more to our world than what we see on the surface. So much mystery waiting to be discovered. So much beauty hiding in unexpected places. The deep ocean teaches us that life is resilient, adaptable, creative beyond measure. It shows us that even in the most extreme environments, in darkness and cold and crushing pressure, life finds a way. And that is perhaps the most comforting thought of all. A reminder that existence is persistent, that beauty exists even in the abyss, that our world is full of wonders we have only begun to comprehend. Good night.